Hello and welcome to 7.2, which is integration by parts. Now, integration by parts is going to help us integrate products where U substitution is just not going to be enough. Now, this is the formula, so to speak, for the integration by parts. Now, this isn't a typo. You're looking at the original integral as U times dV. That's going to equal U times V minus the integral V du. And hopefully this V du integral will be something we can integrate. So when we're looking at the original piece, you're looking at this integral and you're asking yourself, can I integrate it as is? If the answer is no, will a simple U substitution work? If the answer is no, then you're thinking integration by parts. And you're going to look at the U and the dV separately. So you're going to split apart that product, kind of like we did when we were doing derivatives. So the U, you're going to look at that, and hopefully, if possible, it just makes it easier if you can let U be something that gets smaller. So if you've got an x squared or an x or something like that, that makes a perfect U. Now the dV, that's the trickier guy. dV, you have to pick that to be something you can take the integral of. Because when you find dV, you are going to need to integrate that to find the V. So this has to be something you can integrate. So dV is never going to be a natural log. We can differentiate it, so it could be a U, but it can't be a dV. All right, so here's our game plan, basic. When you look at integrals of fractions, at this point right now, if you can't divide it, you can't do a U substitution, you're going to think those inverse trig functions. We are going to learn one additional method for integrating fractions. If you have a product and you can't multiply it yourself, you can't use a U substitution, then you're going to think integration by parts. So when we first started integrals and I had said we don't have a product rule, we don't have a quotient rule, we kind of have things that will help us with those same things in integrals. All right, so we're looking at our first example. We had x e to the x. Okay, and this is a perfect, wonderful example of integration by parts. I couldn't do a basic U substitution because e to the x would have been my u, which meant my du would have just been dx. I wouldn't be able to mess with this x. So it's perfect for our integration by parts. Now this one, when you're looking at the u, I can integrate and differentiate both of those, but x gets smaller. So I'm going to pick u as x, so I need to take the derivative. So you go straight down here. Well, the derivative of x is 1 dx. The other guy is going to get to be dv, so that's all dv is e to the x dx. If I integrate e to the x dx, I get my e to the x. Notice you're going to hold your c till the very, very end. Okay, so now that we've got u dv is what we started with, out in front you're going to have u times v, so that's just this guy right here. So this right here, I'll choose purple. So this right here is my u times v, and then here's my integral of v du. So this is u times v, and this is my integral of v du. Okay, so it kind of makes a nice little zigzag here. So you have your u dv, and then out in front you're going to have your uv, and then inside your integral you're going to have your v du. And then hopefully this is something you can integrate, and we can. So this is our entire answer. X e to the x minus e to the x plus, of course, your c. So let's look at another example without so much yuckiness. When I look at this number 2, I have x squared, I have natural log of x dx. Now remember when we were looking at the u and we said, gosh, it would be great if u could get smaller. Well, x squared does get smaller, but I have the natural log of x. So the natural log of x has to be the u because I can't integrate it. That's what's causing us the problem. So unfortunately, even though x squared gets smaller, it would be a beautiful u. It can't because the natural log of x trumps it. The derivative of natural log of x is 1 over x dx. And then over here, that gets to be our dv. And then we're going to integrate that, which is going to be x to the third over 3 plus c, but we're going to hold off on that plus c. So I'm going to rewrite my integral. Okay, so I'm just going to rewrite it so you can see all the pieces together. You're going to do u times v, so that'll be 1/3 x to the third times the natural log of x minus the integral of v du. So that'll be x to the third over 3 times 1 over x dx. So of course I'm going to simplify that. So that's going to be my 1/3 x to the second dx. So when I integrate that, I have my minus 1/3 times x to the third over 3 plus c. And of course, rewrite that as nice as you possibly can. They may factor out some x's, so just be aware of that for your multiple choice answers. Okay. So when you're looking at who gets to be u, it has to be something that gets smaller, or whatever you can't integrate, that's going to have to be your u. Okay, so let's look at another one. Oh, number 3. Now number 3 is very similar to the one we just did, only it's a little weird because you feel like you run out of stuff, but you don't. Whenever you see a natural log of x, that automatically has to be u each and every time. Okay, because you can't integrate it. Now, the problem, and it's really not a problem, it's all you have left over is dx. So that gets to be your dv. Well, natural log of x, I can integrate or differentiate that. That's 1 over x dx. I can integrate dx. That's just going to be x. So when I rewrite this integral, the integral natural log of x dx is going to equal u times v, so x natural log of x minus the integral of v du. So when you integrate that, you have those x and 1 over x cancels, you have dx. So when you integrate, it's a beautiful thing. Plus c. Don't forget plus c. If you have an integral and you don't have limits upper and lower, you better have a plus c on there. Okay? So if you see a natural log of any kind, a log of any kind, it has to be the u. Anything you have left over, and even if that's just a dx, that's what you got left over, that is what gets to be your dv. All right, so number 4, how exciting. Well, x sine of x, good news is I can integrate and differentiate both of those. So this is one of those game plans where, hey, I'm going to let the u be the guy that gets smaller because his derivative is going to be just dx. So when in doubt, if you can integrate and differentiate both of them, then let the u be the guy that gets smaller. Now it's very important that you be careful here because you are integrating and differentiating in the same problem. So the integral of sine is negative cosine. Okay, so just be very careful. All right, so I started out with x sine of x, which I could not integrate with a simple u substitution. So u times v, so negative x cosine of x minus the integral, ooh, and I have a negative cosine. I'm just going to write it out here. Those negatives, of course, are going to simplify. So that's going to give me a negative x cosine of x plus sine of x plus c. All right. So not too bad. Maybe. Okay. Now on this slide right here, I would like for you to tell me which of the following are you going to use integration by parts, which I have abbreviated IBP, and which ones you are not going to use integration by parts. So stop the video, decide. Okay, hopefully you have taken a look at all of these. Okay, which one of these are you going to use an integration by parts? POW, we need an IBP here, and we need an IBP here. This is just a U sub, and this is a U sub with a backward substitution.